When sizing the ground wire to the secondary side panel, you should indeed base your calculation on section 250.66 of the National Electrical Code. The conductor in question is an equipment grounding conductor. In the scenario with parallel feeds to the secondary side panel, you still size the ground to the panel based on section 250.66, in which case the ground in each raceway is based on the total circular mils of all conductors per phase. Consider the specific example of a 112.5 kV ampere 480 volts to 208 volts dry type transformer feeding a 208 volts panel with a 400 amps main breaker. The system bonding jumper is installed at the transformer, and the panel is supplied by two sets of 3/0 conductors and a ground. The correct size for the ground is number 4. Here's why the total circular mils of all conductors per phase is calculated by multiplying the circular mils of a single 3/0 conductor by the number of parallel conductors per phase. Each 3/0 conductor has a circular mil area of 336,400 circular mils, often abbreviated as kcmil, and since there are two sets of 3/0 conductors, the total circular mil area per phase is 2 times 336,400, which equals 672,800 circular mils. According to section 250.66 of the NEC, which provides guidelines for sizing grounding electrode conductors, the minimum size grounding electrode conductor for an installation with a total circular mil area of 672,800 is number 4 American wire gauge or AWG. Section 250.66 dictates the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Note that the equipment grounding conductor is sized differently based on the overcurrent device protecting the circuit according to NEC section 250.122. Section 250.102 addresses the sizing of bonding jumpers, differentiating them from grounding electrode conductors, which are covered by section 250.66. In this scenario, the conductor in question is an equipment grounding conductor, not a bonding jumper. To summarize, the equipment grounding conductor should be sized according to the total circular mil area of the phase conductors, adhering to section 250.66. For a 208 volts panel fed by parallel 3/0 conductors from a 112.5 kV ampere transformer with a 400 amps main breaker, and number 4 AWG ground wire is the appropriate size. Let's further elaborate on the relevant sections of the National Electrical Code, commonly referred to as the NEC, that govern the sizing and installation of grounding and bonding conductors in electrical systems. Firstly, section 250.66 specifically addresses the sizing of the grounding electrode conductor for alternating current or AC systems. The grounding electrode conductor connects the grounded conductor, typically the neutral, or the equipment grounding conductor, or both, to the grounding electrode system. The size of this conductor is determined by the size of the service entrance conductors. The NEC provides a table, typically table 250.66, which correlates the size of the service entrance conductors to the minimum size of the grounding electrode conductor. Note that this table is used when the grounding electrode conductor is connected to a rod, pipe, or plate electrode. If the grounding electrode conductor is connected to a concrete encased electrode or a ground ring, different rules may apply. Secondly, section 250.102c addresses the sizing of equipment bonding jumpers. An equipment bonding jumper is used to connect two or more portions of the equipment grounding conductor, or to connect the equipment grounding conductor to the grounded conductor at the service equipment. The size of the equipment bonding jumper is based on the size of the circuit conductors and is determined using table 250.102. This table provides the minimum size of the bonding jumper based on the size of the largest ungrounded conductor in the circuit. It is important to distinguish between the grounding electrode conductor and the equipment bonding jumper, as they serve different purposes and are sized differently. The grounding electrode conductor connects the electrical system to the earth, while the equipment bonding jumper ensures a low impedance path for fault current to return to the source. In the given example, The conductor in question is the equipment grounding conductor that runs from the transformer to the secondary side panel. Since the system bonding jumper is installed at the transformer, this conductor is responsible for carrying fault current back to the transformer in the event of a ground fault. Therefore, it must be sized according to section 250.66, based on the total circular mil area of the service entrance conductors. Now, let's consider the scenario with parallel conductors. When parallel conductors are used, the equipment grounding conductor must be sized based on the total circular mil area of all parallel conductors in each phase. This is because the equipment grounding conductor must be capable of carrying the full fault current that could flow in the event of a ground fault. The NEC provides specific rules for sizing equipment grounding conductors for parallel conductors in section 250.122F. This section requires that the equipment grounding conductor be sized based on the adjusted overcurrent protection device rating for the parallel conductors. In the example provided, the panel is fed by two sets of 3/0 conductors. Each 3/0 conductor has a circular mil area of 336,400 circular mils. Since there are two sets of 3/0 conductors, the total circular mil area per phase is 2 times 336,400 circular mils, which equals 672,800 circular mils. Consulting table 250.66, we find that a conductor with a circular mil area of 672,800 circular mils requires a minimum grounding electrode conductor size of number 4 AWG copper. Therefore, the equipment grounding conductor running from the transformer to the secondary side panel must be at least number 4 AWG copper. Now let's discuss some common mistakes when sizing grounding and bonding conductors. One common mistake is to confuse the grounding electrode conductor with the equipment bonding jumper and to size them using the wrong table in the NEC. Another common mistake is to neglect to account for parallel conductors when sizing the equipment grounding conductor. It is important to remember that the equipment grounding conductor must be sized based on the total circular mil area of all parallel conductors in each phase. Another area of confusion is the application of the exception in 250.66a. This exception allows for a smaller grounding electrode conductor to be used when it is connected to a concrete encased electrode or a ground ring. However, this exception only applies under specific circumstances, and it is important to carefully review the requirements before applying it. In summary, sizing grounding and bonding conductors requires careful attention to detail and a thorough understanding of the relevant sections of the NEC. It is important to distinguish between the grounding electrode conductor and the equipment bonding jumper and to size them according to the appropriate tables in the NEC. When parallel conductors are used, the equipment grounding conductor must be sized based on the total circular mil area of all parallel conductors in each phase. By following these guidelines, you can ensure that your electrical system is properly grounded and bonded, and that it provides a safe and reliable path for fault current to return to the source. To further clarify, let's consider the application of NEC section 250.122, which deals with equipment grounding conductors. This section specifies the minimum size of equipment grounding conductors for various circuit sizes. The size of the equipment grounding conductor is based on the rating of the overcurrent protective device, such as a circuit breaker or fuse, protecting the circuit. Table 250.122 provides the minimum size of the equipment grounding conductor for different overcurrent device ratings. For example, if a circuit is protected by a 20 amp circuit breaker, the minimum size equipment grounding conductor is number 12 AWG copper. If a circuit is protected by a 60 amp circuit breaker, the minimum size equipment grounding conductor is number 10 AWG copper. It is important to note that the equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. This ensures that the equipment grounding conductor provides a low impedance path for fault current to return to the source. In the case of parallel conductors, the equipment grounding conductor must be sized based on the adjusted overcurrent protection device rating for the parallel conductors, as specified in section 250.122F. This means that if you have two sets of parallel conductors, each protected by a 200 amp circuit breaker, the equipment grounding conductor must be sized as if the circuit were protected by a single 400 amp circuit breaker. Using table 250.122, we find that a 400 amp circuit breaker requires a minimum equipment grounding conductor size of number 3 AWG copper. Therefore, in this case, the equipment grounding conductor must be at least number 3 AWG copper. Now let's consider the role of the system bonding jumper. The system bonding jumper is used to connect the grounded conductor, typically the neutral, to the equipment grounding conductor at the service equipment. This connection ensures that the equipment grounding conductor is effectively grounded and that it provides a low impedance path for fault current to return to the source. The size of the system bonding jumper is based on the size of the service entrance conductors and is determined using table 250.102 cone. This table provides the minimum size of the bonding jumper based on the size of the largest ungrounded conductor in the circuit. In the example provided, the system bonding jumper is installed at the transformer. This means that the grounded conductor, typically the neutral, is connected to the transformer enclosure, which is then connected to the equipment grounding conductor. This connection ensures that the transformer enclosure is effectively grounded and that it provides a low impedance path for fault current to return to the transformer. It is important to note that the system bonding jumper must be large enough to carry the full fault current that could flow in the event of a ground fault. Therefore, it must be sized according to the requirements of table 250.102 cone. In summary, the proper sizing and installation of grounding and bonding conductors is essential for ensuring the safety and reliability of electrical systems. It is important to understand the different types of grounding and bonding conductors and to size them according to the requirements of the National Electrical Code. By following these guidelines, you can minimize the risk of electrical shock and fire and ensure that your electrical system operates safely and efficiently. Let's delve deeper into the specific requirements for grounding electrode conductors as outlined in section 250.66 of the NEC. The grounding electrode conductor, as we've established, connects the electrical system to the earth. This connection is crucial for providing a path for fault current to flow back to the source, tripping the overcurrent protective device and energizing the circuit. The size of the grounding electrode conductor is primarily determined by the size of the service entrance conductors. Table 250.66 provides a clear correlation between the size of the service entrance conductors and the minimum size of the grounding electrode conductor. However, there are some nuances to consider. Firstly, the table specifies minimum sizes for copper and aluminum conductors separately. It's crucial to select the appropriate column based on the material of the service entrance conductors. Secondly, the table distinguishes between different types of grounding electrodes. For example, if the grounding electrode is a rod, pipe, or plate electrode, the table specifies a minimum size for the grounding electrode conductor. However, if the grounding electrode is a concrete encased electrode or ground ring, the rules may be different. In the case of a concrete encased electrode, the grounding electrode conductor is typically required to be at least number 4 AWG copper. This is regardless of the size of the service entrance conductors. This is because concrete encased electrodes provide a very effective connection to the earth, and a smaller grounding electrode conductor is sufficient to carry the fault current. Similarly, for a ground ring, the grounding electrode conductor is typically required to be at least the size of the ground ring conductor itself. The NEC also provides some exceptions to the general rules for sizing grounding electrode conductors. For example, section 250.66 allows for a smaller grounding electrode conductor to be used if it is connected to a concrete encased electrode or a ground ring. However, this exception only applies under specific circumstances, and it is important to carefully review the requirements before applying it. Another important consideration is the material of the grounding electrode conductor. While copper is the most common material, aluminum is also permitted under certain conditions. However, aluminum grounding electrode conductors must be sized larger than copper conductors to provide the same level of performance. Additionally, aluminum grounding electrode conductors must be protected from corrosion, especially when they are in direct contact with the earth. In summary, sizing grounding electrode conductors requires a thorough understanding of Section 250.66 of the NEC. It is important to consider the size of the service entrance conductors, the type of grounding electrode, the material of the grounding electrode conductor, and any applicable exceptions. By carefully following these guidelines, you can ensure that your electrical system is properly grounded and that it provides a safe and effective path for fault current to return to the source. In the context of the example provided, where a 112.5 kVA 480 volts to 208 volts dry type transformer feeds a 208 volts panel with a 400 amps main breaker, and the panel is supplied by two sets of 3/0 conductors. The key is to correctly apply Table 250.66. As we've established, the total circular mil area of the parallel 3/0 conductors is 672,800 circular mils. Consulting Table 250.66, we find that service entrance conductors with a circular mil area greater than 500,000 circular mils but not greater than 1,100,000 circular mils require a grounding electrode conductor of at least number 4 AWG copper. Therefore, the equipment grounding conductor running from the transformer to the secondary side panel must be at least number 4 AWG copper. This assumes that the grounding electrode is a rod, pipe, or plate electrode. If the grounding electrode is a concrete encased electrode, the grounding electrode conductor could potentially be smaller, but it must still be at least number 4 AWG copper. Now let's address the concept of bonding versus grounding. Grounding refers to connecting an electrical system or equipment to the earth. This provides a path for fault current to flow back to the source, tripping the overcurrent protective device and energizing the circuit. Bonding, on the other hand, refers to connecting different metal parts of an electrical system together. This creates a low impedance path for fault current to flow, minimizing the voltage difference between the bonded parts and reducing the risk of electrical shock. In the example provided, the system bonding jumper is installed at the transformer. This connects the grounded conductor, typically the neutral, to the transformer enclosure and the equipment grounding conductor. This ensures that the transformer enclosure is effectively grounded and that it provides a lower impedance path for fault current to flow. It is important to note that bonding and grounding are both essential for electrical safety. Grounding provides a path for fault current to return to the source, while bonding minimizes the voltage difference between different metal parts of the electrical system. By properly bonding and grounding your electrical system, you can significantly reduce the risk of electrical shock and fire.